Okay, you're on the right track. It's not just mass by itself, but it's X-rays reaching the image receptor. X-rays are signal. And it's not just X-rays overall, but X-rays specifically that make up the image. So remember, some of the X-rays that hit the image receptor are scatter. And scatter is not signal. Scatter is noise. So when we look at signal to noise, we're looking at a comparison of X-rays that make up the image hitting the image receptor to other things that impact the image influencing the image receptor. So some of those things will be static in the digital system. Some of those things will be scatter. Some of those things might just be stray radiation from other sources around, like the bricks that the building is made of. All of those things contribute to noise. Okay, so when we talk about signal to noise, we're talking about when we look at an image, we compare signal or X-rays that make up our image to the other things in the image that take away from the image, like scatter. So a way that you could enhance SNR, or signal to noise ratio, would be to get more X-ray signal or to get less noise signal. Well, something that a lot of people don't understand is that noise is always present in an image at some level. And it's usually pretty consistent. So even when you do images of different people, the amount of scatter that you really see in the image is pretty consistent from person to person. The amount of static from the electronics in the system is almost always consistent throughout from image to image. So really what you can do to enhance signal to noise is increase the X-ray signal in the image. Okay, and this is one of those places where we talk about dose creep, and you've heard me say those words before, dose creep. And so what has happened, the reason that dose creep has happened is because people start talking about signal to noise, and they say, well, if I can get a good image with 10 mass, but there's a little bit of noise in it, then I can make that noise disappear. It'll still be there, but you won't be able to see it if I go to 20 mass. And so they're increasing the signal to noise ratio. The problem is they're also increasing patient dose. So most of the things that we do to increase signal to noise ratio increase patient dose. So another thing you could look at, another way to increase signal to noise ratio would be, instead of increasing signal, to decrease noise. And one of the ways we can decrease noise is by using a grid. But when I put a grid in place, I have to turn my mass up to counter the effect of the lost X-rays. So I take out some noise, but then I have to turn up the mass. And when I turn up the mass, what happens to patient dose? Goes up. So again, I have increased signal to noise ratio, but I have also increased patient dose. So most things that increase SNR also increase patient dose. Okay? Again, remember that noise is pretty consistent. There's always some level of noise. So you have noise right here. And the idea is to get signal above that level so that you can see the image. And the higher above the level of noise you get, the more image you see. And that's an increase in SNR. And I don't want you to make it any more difficult than that. You're not going to have to do any calculations of SNR. All you need to understand is how it works. Signal is X-rays that make up the image reaching the image receptor. Noise is everything that takes away from the image. So we want to have the best signal to noise ratio that we can, but we don't want to increase it at the expense of patient dose. Okay?
Hey, Roger, real quick with that though, what about the contrast to
Okay, there's also something called contrast to noise ratio, or CNR. And contrast has nothing to do with signal. Okay, you have to keep them separate. Signal to noise ratio and contrast to noise ratio are not the same thing. Contrast to noise ratio is the ratio of different steps of signal compared to the overall noise. And again, there are things that you can use to increase contrast to noise ratio, like a grid, but you're probably not going to see much on the registry about contrast to noise. It's just not something that we talk about much in X-ray imaging. We talk about it in other modalities a lot, especially in MRI, but we don't talk about it as much in radiography because we have much less control over it in radiography.
that?
Okay, then the next thing that she wanted to talk about was dynamic range. And dynamic range, let's see, where am I looking? Go the wrong thing. There we go. So I'm going to explain dynamic range in two different ways. First, I'm going to talk about how we would think about dynamic range with film imaging. And so in film imaging, we had these graphs that were called Herter and Dreifield, or H&D curves. And they compared optical density to exposure. And sorry, it's really hard to write with a mouse. Hard for me anyway. Maybe it's not hard for you, but it's hard for me. Especially on this very picky whiteboard. Okay, so optical density and exposure. And in film imaging, what we would do is we would take a box of film, and we would take one piece of film and we load it in a cassette, and we'd set our mass and KVP at a standard setting, and we would expose the film and we would develop it, and we would measure its optical density. And we would do this over and over and over again with different boxes of film. That's one way we could do it. Another way we could do it would be to take, you remember the penetrometer that I showed you, the step wedge that had there was an aluminum block that was cut into steps? So we would use that, and we would just make one exposure with that, and we would measure the optical density of each of the steps. And then we would graph that density, and we would get a graph that would look something like this. And what we were measuring was the useful range of density. So the lowest density that we can see is 0.5, and it's not taking my point for some reason. 0.5. And the darkest density that we can see with our eyes is 2.5. So we called the range 0.5 to 2.5 the useful range of densities. Anything lighter than 0.5 just looked white. Anything darker than 2.5 just looked black, and we couldn't tell those differences. So those were the densities that we were concerned about with film imaging. And what we would do is we would graph this like this, and then we would measure across. We just take a straight edge. We'd go straight across the graph, and then we'd measure down, and we would see the minimum exposure that would produce the minimum density. And then we would do the same thing with the maximum density. We would just mark it across there. And we would find the maximum exposure. And that maximum exposure is what would give us the maximum density that we could see. And in between that, we called that latitude. Now, in the digital world, that's called dynamic range. And different types of film had different slopes of that graph. So they may have a really narrow dynamic range or a narrow latitude, or they may have a really wide latitude. But the difference when we went to digital imaging, digital image receptors have an H and D curve that's just a straight, much straighter than what I can draw, but it's just a straight line like that at a 45-degree angle. And when you measure the range of exposures that produces that useful range of densities, so this is the range, this is the exposure that gives us 0.5 density, and we measure this on across, and this is the exposure that gives us 2.5 density. So this range of exposures is called the image receptor's dynamic range. And it's just the range of exposures that produces the usable range of densities that we can see with our eyes. Now, because we can use bit depth to control that range, we're not so concerned about range of exposures, but that's still called dynamic range. And so that's why you've seen those words. I don't use them much because we just don't talk about them very much anymore. But dynamic range is just the range of exposures that produces the useful range of densities on the image. And it's a quality control test. Just a quality control test. So what we'll do is we'll take the step wedge, we'll put it on an image receptor, we'll make one exposure, and under the thickest part of the step wedge will be the lightest exposure, and under the thinnest part of the step wedge will be the darkest exposure. And each step is a half value layer, so it's a doubling or a halving of exposure. And so we just make this graph, and this is where dynamic range comes from. But it's really hard to understand what it actually is. But again, it's the range of exposures. Everybody sees that this bottom scale is exposure. So it's the range of exposures that produces the range of densities that our eye can see. And our eye can see from 0.5 to 2.5 density. So if I had, let me see if I can get this whiteboard to work enough. So if I had a graph that had a sharp curve like that on it, then you can see the range of exposures here. Let's see. Here is the exposure that gives me 0.5. And about right here is the exposure that gives me 2.5. So my dynamic range is really narrow. Can everybody see that? Can you see that how narrow the dynamic range is?
Yeah.
Yes. And that's just a function of the slope of the graph. So a steeper slope gives you a narrower dynamic range, and a shallower slope gives you a wider dynamic range. So that was the advantage to digital imaging, is it gave us a really wide dynamic range. So that what this means is, as long as my exposure, my KVP and mass, falls somewhere within this wide, the red exposure range, as long as it falls somewhere within there, I'm going to get a good image. I'm going to get a usable image. But if I was looking at the blue graph, then my range of exposures that produce a good image is much narrower. I have to be much better controlled with my KVP and mass. But with digital imaging, it gave us that wide dynamic range. That red graph that I drew there gave us that wide dynamic range. And so we don't have to be nearly as precise with our KVP and mass to still get a good image. And that's all that we're talking about when we talk about dynamic ranges. Specifically in digital imaging, it's how much easier it is to take an image because we don't have to be as tightly controlled with our KVP and mass. So, and you'll hear techs say that all the time. Oh, I would use 70 kVp at 3 mass, and somebody else will say, oh, I would use 80 kVp at 2 mass, and either one of them would give them a good image. They're both right because we use digital systems, and the system is really flexible because it has a wide dynamic range. That is the advantage of digital imaging. It has a wide dynamic range.
Roger, I have a question about that. So when we're at, like when we did our rotation through Evans, and they use CR, and at the bottom of the image, you would get a readout between a certain number, and you were supposed to be, they would say, okay, that, you know, that range was perfect. Is that what they're talking about? Is that's their dynamic range?
That's what they think they're talking about, but no, that's not what they're talking about at all. They're completely wrong with that. And you've heard me say that before in class, that the way that Evans did that made me absolutely crazy. It's called an exposure indicator. And what that's telling you is how much radiation reached the image receptor. And each exam is programmed with a range of numbers that would give you a generally okay image without going too high in patient dose. It's a combination of image and dose, where dynamic range is just image. Exposure indicator is a kind of a combination of image and dose. And so you want to stay in that range as much as possible. But if you get a number that's too high, you do not want to repeat the image, because that means you already applied too much radiation. And if you do the image again, what happens to the patient's dose?
It increases.
It increases. It probably doubles. And so you already had too much radiation. And so to take the image again just gives the patient even more radiation. That's crazy talk. That's crazy talk. You should never repeat an image based solely on exposure indicator. You should only repeat an image based on image quality factors. If it's modeled, you should repeat it. If you're losing contrast because your technique was too high, you should repeat it. But you should never repeat an image because of exposure indicators. Exposure indicators kind of feel like dynamic range, but they're not dynamic range. Any of you go to work at Evans? Try and teach them that. Once you're a tech, you can kind of argue with them a little bit. When you're a student, you can't argue with them, but when you're a tech, you can argue with them a little bit. So remember my argument and make it.
Sure. How is the exposure indicator related to the patient's dose?
Well, if I have a higher exposure, well, it depends on the type of exposure indicator. Remember, there are some exposure indicators that are direct relationships, and there are other exposure indicators that are inverse relationships. Different manufacturers use different kinds of exposure indicators. So some manufacturers use what's called an EI, or an exposure indicator or index. And that's a direct relationship between the number and the exposure. So the higher the number, the more exposure you had. So if more radiation reaches the image receptor, then the exposure indicator would read higher. And if you have more radiation reach the image receptor, what does that tell you about radiation that reached the patient?
Yes.
It's going to be higher as well, right? So another type of exposure indicator is called S number, and that's not your student number. S number is an inverse relationship. So the higher the number, the lower the exposure. And so if you have if your S number is too high, that means you didn't have enough exposure and your image might be mottled. But if your exposure number is lower, then that could mean that you used too much radiation to get the image. And that's one of the problems that we have with different manufacturers now, is everybody's using something different. So the FDA is kind of trying to force everybody to go to the system that uses red, yellow, green, or red, orange, green. And if it's green, that means that you're within an acceptable range of exposure indication. If it's red, that means you are either way too high or way too low. And if it's orange, that means your image will probably still be okay, but you're outside of the accepted range. And red and orange don't mean that you're too high. It means that you're outside of the accepted range, either too high or too low. So that's another thing to remember about. A lot of people think it automatically means too high, and that is not the case. Okay, so we kind of changed gears there a little bit. We were talking about exposure indicators, but our original conversation was about dynamic range. So they're not the same thing, but they are somewhat related. So I don't know if that helped at all. Oh, sorry. Told that person specifically not to call me right now. Okay, so the next thing on my list is window width. But actually, before I talk about window width, I'm going to talk about window level. And window level is a control or a measure of image brightness. And I think I've told you this before. The way that I remember it is, if you go in a room and you raise the blinds, you make the room brighter. Well, the same thing is true with window level. If you raise the window level, you make the image brighter. And in most imaging modalities, the way that you raise window level is you take your mouse and you hold the left mouse button down and you move it up or away from you. You move the mouse up on the screen, and that raises window level, and that makes your image brighter. So just remember that window level measures and affects brightness. Window width is a measure of the contrast or the scale of contrast of the image. So if you move the mouse to the left, that usually makes your image grayer, and they kind of tried to keep this consistent. Remember, long and low go together? Well, if you remember that left, long, and low all go together. If you move your mouse to the left, you get a longer scale of contrast or a lower contrast. If you move your mouse to the right, you get a higher contrast or a shorter scale of contrast. So I know that when we talked about CT, we talked about numbers and doing math with window width and window level. And I told you when we did that that's not something that we do in radiography. If you go into CT, that's something that you might have to know. But in radiography, we don't have to know the number part of it. We just use our mouse to window the image if we need to. But then again, remember that in radiography, most systems do not allow you to window without saving. And if you save your window changes, then the radiologist cannot adjust windowing. And he may need to see something, or she may need to see something on the image. And if you save your windowing, the radiologist cannot affect windowing at all. So most facilities won't let you window.
Roger, I think where I got confused on window level is that's what I had written down, that you talked about, like raising the blinds and making the room brighter. But on rad review, it says the exact opposite. It says to increase the brightness, that you drop, or the window level goes down.
No, that's not true.
So I thought I had a good grasp of concept on that, and then I keep getting that one wrong, and it states the complete opposite. So now I'm back to square one, super confused.
Yeah, that sounds like it's a problem with rad review.
Yeah, so when I come across that question again, I'll screenshot it and then send it to their tech support.
Okay.
Okay,
And if they have a reason for explaining it the way they do, then they can explain it better for you.
Okay.
Okay, so what else you got? That's all that Heather had sent me.
A question on pixels, matrices, and and field of view. David was kind of helping me a little bit, like understand. I understand the relationship between matrices and pixels. I don't quite understand what a matrix is. Is that the monitor? I'm not getting what a matrix is exactly.
A matrix is a collection of pixels. So, like, if you were all in the same view on your WebEx stuff, I could explain it even better, because I'm looking at a very perfect picture of how to explain a matrix. But on my side right now, what I'm looking at for you guys is I'm looking at a matrix of 3 of you across the image, and 3 of you down the image. So the box, or the field of view, which is what I can see, the field of view is made up of 9 boxes. So this is a 3 by 3 matrix. And only 7 of the boxes have anybody in them, but it's still a 3 by 3 matrix. And what happened was, when I first logged on, I went to this grid view that I'm looking at, and Frank was the first person to log in, and so he took up the whole field of view. He took up the whole box. Just Frank's box was the whole field of view. So that was a 1 by 1 matrix. Okay, and Frank was really big. And then Cheyenne joined, and it turned into a 2 by 1 matrix, so that there were 2 boxes side by side, but they only made up 1 level. So it was a 2 by 1 matrix, and Frank's box was then cut in half. And then as each of you joined the meeting, it made your individual, and you probably saw this yesterday when we had our little get together yesterday, if you were in this grid view, that as each person joined, their box got smaller. And that's why for the same field of view, which typically in imaging, our field of view is going to be 8 by 10 or 10 by 12 or 14 by 17 or something like that. Those are fields of view. But the matrix is a collection of pixels, and the pixels are arranged in boxes. So the number of pixels across the top or across from side to side and then the number of pixels up and down is the matrix. So a 512 by 512 matrix, which is common in radiography, means that it has 512 pixels across and 512 pixels from top to bottom. So, like if you look at my picture on your screen right now, you can see that it has a number of pixels across this way, and then it has a number of pixels up and down this way. And those numbers are the matrix. And so as the numbers of the matrix goes up in the same, if you have the same area, if your box is the same size all the time, in the same area, if your number of pixels goes up, then the pixel has to get smaller to fit in the same spot. Okay, but the matrix is that, so let me go back to that, what I was at earlier. So if I have a field of view like this, and I start, oops, with 4 pixels, can you see 4 pixels there? Okay, so this is a 2 by 2 matrix. So here's 1, here's 2, and here's 1, and here's 2. So this is a 2 by 2 matrix. And then if we were to divide these pixels in half in both directions, so we divide them in half this way, and then we divide them in half this way. Now we still have the same field of view. So the area of the matrix is still the same size, but we have twice as many pixels. So now this is a 1, 2, 3, 4 by 1, 2, 3, 4. So this is a 4 by 4 matrix. Now if we were to divide the pixels in half again, so see how the pixels are getting smaller, but the field of view is staying the same. Keep making the pixels half the size. Now we have a 1, 3, 4, 5, 6, 7. Oh no, I have too many drawings in there. There we go. 8 by 1, 2, oops, 3, 4, 5. Ooh. Sorry, it's getting hard to write in this little tiny box. 6, 7, 8. So each time that we cut the pixel size in half, we double the number of pixels in the matrix. So like if you were to go to Best Buy and buy the most popular 4K TV right now, that means that it has 4,000 pixels. 4K, K is thousands, so that means it has 4,000 pixels across the top or across from side to side in your image. Okay, that means that the pixel, to have 4,000 of them in there, the pixel has to be really small. Before there were 4K TVs, about the best resolution they could do was at 1028 or pixel size, number of pixels, 1028. So we went from 1,028 pixels across the image to 4,000 pixels. And to do that, the pixel had to get much, much smaller. And when the pixel gets smaller, you get better resolution. Okay, I don't know if that helped at all. I know I've done that before, sort of. But do you kind of understand what a matrix is now?
Yeah, so matrices are dependent on the pixel size.
Correct. And
Okay.
pixel size is dependent on the matrix.
Okay, and so is the field of view, does that have any relationship to the matrix?
No. A matrix is inside the field of view, but the field of view is based on overall area of the anatomy that you're trying to look at. So if you select an image receptor that's 10 by 12, then your field of view is 10 by 12, 10 inches by 12 inches. And then the matrix is determined by how many pixels fit in that 10 by 12 field of view.
Pixels would depend on the monitor that we
Right.
would see. Okay, gotcha.
Hey Roger, how does bit depth play into the pixels?
How does bit depth what?
Pixels.
Bit depth doesn't affect pixels. Pixels measure bit depth. So when we talk about bit depth, we're talking about how many shades of gray each pixel can display. So if my pixels have a bit depth of 4, for example, then I take 2 and raise it to the 4th power, because it has a bit depth of 4, and that means that each pixel can display 16 shades of gray. Okay, but it has nothing to do with the size of the pixels. It just has to do with how many shades of gray it can display. Okay, so does that make sense?
Does, thank you.
Does you think?
I have a quick question, Roger.
Okay.
In Bouchong, I don't know if this applies only to CAT scan. There's a little part of it where it says when the field of view is increased for a field matrix size, for example, from 12 centimeters to 20 centimeters, the size of each pixel is increased proportionally.
Right. That would be true. We don't ever talk about that in radiography, but that would be true. If you increase the field of view, then and you keep the matrix the same, then the pixels are going to get bigger, right? Because they have more room to spread out. So the pixels would get bigger. So that is true. But I wouldn't worry about that with radiography.
That's only with CAT scan.
Well, it happens with any imaging modality. They're just not going to ask you about it in radiography.
Oh, okay. Well, I have another question if no one else wants to go.
It sounds pretty quiet to me, so you might as well go.
All right. Can you kind of briefly go over the thresholds, like linear and nonlinear,
Okay.
and just where they're at on the graph again?
And would
Okay.
you also, with that, Roger, I mean, when you went over it in class, it made perfect sense, but there are some questions on rad review I'm having a difficult time remembering or understanding, like what constitute as linear or nonlinear. The threshold and non-threshold I'm good with, but the linear and non-linear, I don't know where those fall and exactly what details go with those.
Okay, fortunately, that's easy to fix. So if we have a graph, come on. We have a graph that has dose across the bottom and effect. I'm not going to write the whole word. There we go. That's effect. Then we can create a dose-response relationship. So instead of effect, you could also call that response, but sometimes that's confusing. So first, if I have a graph that is a straight line, any degree of straight line, that is a linear graph. Okay, if the line is straight, it's linear. Okay, if the line is not straight, that's nonlinear. Any of those that are not straight are nonlinear. Okay, so straight lines are linear graphs. Crooked lines are nonlinear graphs, and that's all you have to remember about that. Now, if we look at all of these different lines that I just drew on the page, then this first line, see if I can do this without it. So this line right here, if I trace that all the way back, it would hit the x-axis or the y-axis, right? It would hit right about 0. That means that it's non-threshold, because that means that if I get any dose above 0, then I get a response. I have the effect, whatever that effect might be, whether it's cataracts or skin cancer or whatever, a burn, any of that. If I have, if any amount of dose at all will cause the effect, that is a non-threshold dose-response relationship. If, on the other hand, I have a graph, so let's look at this graph. And I drew this crazy graph on purpose. Notice that it doesn't start at 0. It has some degree of dose, so I can go this far over on the dose line before I start seeing that effect happen. Does everybody see that?
Yeah.
Okay, so that would be a threshold response. And if you just think about it, the door to your house, the front door to your house on the ground has a threshold. And it's called a threshold because it divides when you're outside of the room or when you're inside of the room. If you're outside of the threshold, then you're going to be out in the weather. And if you're inside of the room, then you are inside the effect of the house, which means you're protected. Now, in radiography, doesn't mean you're protected. It means once you get above the threshold, you're prone to the effect or to the response. But the threshold just means that below the threshold dose, you don't get the response. And above the threshold dose, you do get the response.
Roger, can you provide a couple of examples on what would be linear and nonlinear, like cancer, cataract, skin
Sure.
just view for each?
Sure. Cancer is a linear dose-response relationship. As the dose goes up, the rate of cancer goes up. So it is a linear dose-response relationship. Skin burns is a nonlinear dose-response relationship. Cataracts is a nonlinear dose-response relationship. Probably the most common dose-response relationship that we need to worry about is cancer, because that would be the one thing that we would be prone to as radiographers, or that we used to be prone to. We're really not anymore, but we used to be prone to cancers. And so it was what we were really taught about was linear or non-threshold dose-response relationships, because those were the kind of exposures that we got every day at work. We got exposed to low doses, and we had to worry about effects that were caused by really low doses and had a linear response rate. Okay? Rarely do we as a technologist need to worry about getting a skin burn because we're not in the primary beam, but we do need to worry about that for our patients. But we know that there's a threshold, that if we're below that threshold, then we don't have to worry about it. So in fluoro, we keep track of dosages. One of the things that we have to fill out on our fluoro report every day is a dose that we gave. Because if we get above the threshold dose, we have to start worrying about skin burns. When the dose first starts out above the threshold, the response rate is really low, and then it just really shoots up dramatically. And then remember that at some point, the skin is all dead. You can't kill it anymore, so then it levels off again. So that's why you get a nonlinear dose-response relationship with something like a skin burn.
Do you think that we'll need to know the tissue weighting factors for like bone marrow and liver and brain, or do you think if we have questions they'll provide
You
that?
don't need to know the numbers. They'll give you the numbers that you need to know. You need to be familiar with the equations. And I'm not saying that you need to memorize the equation. I'm saying you need to be familiar with the equation.
Roger, I came across this question on Rad Review, and I just want to make sure I'm on the right track. So it says the late effects of radiation, carcinogenesis, and embryologic effects are considered 2, and it has 1, 2, and 3. So have no threshold dose, be directly related to dose, and 3 is occur within hours of exposure. So I put that they have no threshold dose and that they're directly related to dose, and that was wrong. And so
That was
I guess
wrong?
it said it was just that it has no threshold dose.
Well, it definitely has no threshold dose.
Uh-huh.
But it is a direct relationship to exposure. As exposure goes up, the effect goes up.
Okay.
You are not instilling confidence in Rad Review easy in.
Aren't in us either.
Speaking of that, Roger, I got a question for you from Rad Review.
Okay.
So this is like we were talking last week about the anode heel effect. Which of the following combination of factors will cause?
You're breaking up a little bit, Garrett. I can't hear you.
Okay, so which of the following combination of factors will cause the anode heel effect to be more pronounced?
Okay.
And the answer is small anode angle, short SID, and large field size. Can you explain that?
So what was the first part of the answer?
Small anode angle.
Okay. So small anode angle means, Draw you a picture. So a small anode angle would be an angle like this. Okay, so here is the, oops, forgot again. Here is the angle of the anode. This is a small anode angle. So remember, what causes the heel effect is when electrons from the cathode get back here into the back of the anode, into the heel of the anode, and produce X-rays. And since the anode is made of metal, those X-rays can't get out to get down towards the patient. They get absorbed by the anode. They're created, but they're absorbed by the anode, so you have fewer X-rays on that anode side. But if I have a small anode angle, then the same thing would happen if I had an electron interact right here, wouldn't it? Because the X-ray would have to travel through almost the same amount of metal. So a small anode angle would give me more anode heel effect. Remember, most anodes are shaped more like this. Okay, so that's a bigger anode angle. And so there's less heel of the anode, the back side of the anode. There's less heel because there's more angle. Okay?
Okay.
The other part of that is field of view, right?
It's yeah. The only other two were short SID and large field size.
Okay, so SID would affect heel effect. So let's clarify that right now. SID will affect heel effect, but if it's long SID will make more pronounced heel effect. So a short SID will not make a pronounced heel effect.
Oh,
But a larger field size means that we take a cassette and we put it down here underneath the anode. Well, if I have a larger field size, well, let's start with the smaller field size first. So let's say that I'm just using this side of the image receptor. So my X-rays on the anode side come down here, and my X-rays on the cathode side come down here. If I have a small field of view, or if I have a small field size, then the X-rays fill up the entire image receptor. Okay, but if I go to a larger field size, then the X-ray fields still only spreads out the same amount. But if I have a bigger field, the X-ray field can't fill the entire image receptor. So I can see the effects of the heel effect on the edges of the image. I know that doesn't make any sense. I cannot explain it the way that I'm showing it in this horrible whiteboard. I can't make it make sense to you. But when the field is small, when I have a small field size, the X-ray field is all taken up by the image. When the X-ray field is bigger, when I go to a bigger field size, then the image doesn't take up as much X-ray field. Because remember, we're not trying to fill the entire cassette with image. We're only trying to take an image of the structure. So what happens is the angle of the, so remember I have on the anode side, I have the X-ray beam is almost straight up and down. And on the cathode side, the X-ray beam is at an angle. So if I have a bigger field size, then those differences in angles are more apparent on the image. And I know that didn't make any sense. I really cannot explain it with this equipment the way we're set up right now. But if you take, let's see. If you take a flashlight See if I can make this work so you can see what I'm talking about. If you take a flashlight, so I'm not going to change the field size. I'm going to change angle so that you can see what's happening. Okay, so right now the image, which is the circle of light, is really small, right? Can you see that on that image?
Yeah.
But
Yeah,
when I make an angle more pronounced, then see how much bigger the image gets? Because it gets elongated. The same thing happens when we're talking about heel effect, because what we're dealing with is an angle of X-rays. The X-rays are angled as they leave the tube differently. The X-rays on the anode side are more straight up and down. The X-rays on the cathode side are at more of an angle. So if I expand my field size, I make that more apparent. It's easier to see that it's happening. It's hard to see it happening anyway because the anode heel is so small to begin with. It's really hard to see it happening, and that's why it's so hard to grasp, because you just can't see it. But if you think of the three things that that question gave you as choices, it gave you small anode angle, which I drew as much of a picture there about that as I could. It gave you short SID, but remember, a long SID pronounces the heel effect. And then it gave you a larger field of view, or a larger field size. And a larger field size will give you a more pronounced heel effect because of the angles involved.
okay, thank you, Roger.
Yeah, I wish I could explain it better than that.
But it seems like they're wrong though, as in they said short SID when it should have been a long SID. It's more pronounced.
A long SID is more pronounced.
So, but they say it's a short SID.
No, they gave you that as a choice. But you said it was not. That was not our correct choice.
Oh no, it was.
Oh, okay. You said it was not a correct choice.
Oh, I'm sorry. So yeah, the choices were that it was a small anode angle, a short SID, and a large field size. That's the correct answer. Those three things.
Okay.
So sorry about that, but we can move on. We're good.
Okay. I think you lost me, but okay.
We have all of these resources to help us prepare Rad Review, Rad Tech Bootcamp. I remember you saying the exams on the ASRT and then the HESIs. Which one of these are most related to how the registry is going to be tailored?
The exit exam that you just took Tuesday is most similar to the registry. But a lot of the questions that you've seen on Rad Review Easy, except for the ones that are wrong, a lot of the questions that you've seen on Rad Review Easy are really similar to registry questions. I know there were questions when I took my registry that they didn't have Rad Review Easy, but they had the Lang book, which is the same as the Rad Review Easy. It's just a book instead of an online platform. And there were questions that I had on my registry that I could say were word for word on my registry what they were in my Lang book.
And what would be your opinion on using the ASRT practice exams to help prepare as well?
I don't know. I would think they would be similar, but I've never used them. I would think that they would be really similar, though.
I have a question as well, Roger.
Okay.
For James was telling us that during our registry, the 3 hours we have to take the test belongs to us, in the sense of, like, if we have to step out and use the restroom or get a drink, that we're able to do that. Is that true? Is that untrue? I just know when we took this exit HESI by question 160, I was like capped out. I was burned out, and we're not allowed to get up and walk around or step out to kind of like decompress a little. And I'm just kind of curious, are we able to do that when we take our registry?
Technically, they will not let you get up to just walk around.
Well, not just to
If-
walk around, but like to step out to go to the restroom.
If you need the restroom, don't just get up. Never just get up.
Okay.
Raise your hand and let the proctor know that you need to use the restroom, and they should let you go.
Okay.
But your clock will keep running.
Right.
Okay, but if you need to use the restroom, they should let you do that. 3 hours is a long time.
Well, I just think a little break in that time is mentally is more, I think, more necessary than the restroom break. But I was just kind of curious. I just found by like question 160 in our exit exam that I felt maybe I rushed a little bit through the last 70 questions because I was just starting to get mentally like exhausted and overwhelmed. So I was just wondering what kind of outlet we had as an option up there.
Yeah, they should let you go to the restroom if you need to go to the restroom. So if you just need to get up and move for a minute, then tell them you need to go to the restroom.
Roger, for the calculator that they're going to give us for the registry, is it actually going to be able? Are we be able to square on that?
I don't know.
Because
When
that
I took the registry,
calculator
the answer was no.
Mm.
When I took the registry, it was a junk calculator that was on the registry. But don't worry, you will not need it.
Okay. Okay, sounds good.
They may expect you to know how to do bit depth, but they're unlikely to ask you to do anything with bit depth. And if you just remember, like I told you, that a bit depth of 14 gives you 16,000 shades of gray, then you'll be okay.
Sounds good.
I do have another question. Actually, I think I answered it. Never mind.
Okay.
Just because it's kind of older, can you go over how mass affects wavelengths, please?
Mass does not affect wavelength. That's a great, easy question to answer. Remember, wavelength is related to energy. And mass does not affect energy. Mass affects number of X-rays only. Number of X-rays only. Energy affects wavelength because energy, remember we had the equation E, energy, equals H, HF, I forgot what I was doing because I was thinking, okay, and that doesn't do any good, but it also equals HC over lambda, and lambda is wavelength, right? Remember that? I know it was a long time ago, but
Yeah.
hopefully you remember at least a little bit of what we talked about. So E equals HC over lambda. So if wavelength goes up, since it's on the bottom of the fraction, that means energy goes down. So if you think of it the other way around, if energy goes down, wavelength must go up, right?
Yeah.
Okay? So energy affects wavelength. So energy is controlled by KVP and by filtration.
Yeah, that makes sense. There's quite a few questions on that, and I hadn't studied it in forever.
Yeah, I know there were a bunch of them. I noticed that on your results, on everybody's results, not just your results. I didn't look at any one person very in depth, but I glanced over everybody's just to see what kind of questions were commonly missed. And I saw I saw several of those.
So real quick, Roger, So frequency and wavelength are inversely related, whereas energy and frequency are directly related.
Frequency and wavelength are directly related. Wavelength and energy are inversely related. Frequency and wavelength are inversely related. So if you remember, let me get another board up here real quick. So remember, we have C equals frequency times wavelength. And that's the speed of light equals frequency times wavelength. What changes the speed of light?
Nothing.
Nothing. Good. Nothing. So if the speed of light is constant, if frequency goes up, wavelength has to go down to keep the speed of light constant, right? Does that make sense?
I got it.
Makes sense.
Okay. So that means that for EM radiation, frequency and wavelength are inversely related. Okay. And we also had Planck's equation that says energy equals Planck's constant times frequency. Okay, since we're just multiplying, if frequency goes up and Planck's constant stays constant, what has to happen to energy?
It goes up.
It also has to go up. So that means that energy and frequency are directly related. If one goes up, the other one goes up. Okay? So then we also have the equation. This whiteboard is horrible. Energy equals HC over lambda. So H is constant, it's Planck's constant, and C is constant, that's the speed of light. So those two don't change. So since wavelength is on the bottom of the fraction, if wavelength goes up, energy has to go down. And the way that I always demonstrate that is if I have a fraction, I have the fraction 1/2, and then I have the fraction 1/4, and then I have 1/8, and then I have 1/16. Notice the number on the bottom of the fraction is getting bigger, but the value of the fraction is going down as the bottom number gets bigger. That's because in this case, wavelength and energy are inversely related. As wavelength goes up, as the bottom number gets bigger, energy goes down. Or you could say it the other way around. You could say as energy goes down, wavelength goes up. And they will ask you about those relationships. They will, I promise you, they will ask you about those relationships. Does that make sense to everybody?
Yeah, it does.
It does. Thank you.
Good.
Do you think on the registry we're gonna have to calculate the parallel and series circuits?
Nope.
All right.
You need to know them, but you don't need to calculate them. You need to know what the difference is between them. But I wouldn't worry about it. You'll be fine.
For those of you who don't have RadTech Bootcamp, I found after taking our HESI exit exam on Tuesday that a lot of the videos I watched when I got home Tuesday and Wednesday answered all of the questions I know that I missed. So for any of you who do not have it, I think it's still on the spring sale for $22 for the month. I would recommend getting it. It's been super beneficial. And it's covered a lot of the stuff that we haven't went over since the first or second semester. So it's really been helpful.
I have been hearing very good things about boot camp.
Can you kind of go over what to expect, like getting to the registry? Like, I went on their website and went to like their exam day, like what to expect kind of thing. But can you just like make it simpler for me to understand?
At the testing center?
Yes.
Okay. So when you go to the testing center, and it may be a little bit different because of the COVID-19 restrictions, but this is how it typically works. You go to the desk at the testing center and you tell them who you are, and they pull up your record and they check your IDs. And remember, you need 2 forms of ID. One of them needs to be an official government type ID, like your driver's license, and it needs to have a picture on it. The name on your ID has to match your registry application. When we went over that when you did your applications, so you should all be good there. The other ID, they're pretty flexible normally. They'll take social security cards. I've seen them take credit cards, but you really need to check with the testing center to make sure what they will accept as far as a second ID. But they'll check your IDs and make sure that you're you. Then they will take prints of both of your palms. They take electronic images of both of your palm prints. And sometimes they take images, or they fingerprint you as well. It just depends on the testing center's policy. Then they will have you take everything out of your pockets, and again, this may be different because of COVID-19, but they'll have you take everything out of your pockets and put it in a locker and lock it, and they'll let you keep the key. That's the only thing you can take in, just like with the testing center here. Now, it is possible that they may not have lockers for you because of the COVID-19 restrictions. If that's the case, make sure that you don't take anything in with you at all, except maybe your car keys and your IDs. Don't forget your IDs. Okay? Then they'll take you into an exterior room to the testing center, and they'll ask you some questions. They may pat you down to make sure you don't have anything in your pockets. When I took the registry, they also offered us a little checkbook calculator. If you're worried about being able to square things and take the square root, take that little checkbook calculator because it does have those functions on it. If they won't let you take your own calculator, but they will let you use one of theirs if they have them available. They may not have them available again because of COVID-19. Then they'll take you into the testing room, and the testing room is similar to where you took your exit exam. You'll be set up in carrels like that. They'll give you a dry erase board. It's basically a piece of paper that's been laminated and a dry erase marker. Remember, do not erase, and they'll give you these instructions as well. You can fill up the dry erase board all you want. When it's full, raise your hand and ask for another one if you need it. But do not erase. That's considered cheating. So do not erase. Try to avoid talking to yourself while you're taking the registry. They get really nervous when they record you and you're talking. They're worried that you're cheating with somebody, so don't talk. I know that's hard not to do. If you need to move your hands and stuff around to mimic different body planes or different positions, they usually don't get too worried about that because everybody does that. But the testing center is going to give you really good rules about how to ask for restroom breaks and things like that, and how many you can have, all that kind of stuff. So just make sure you pay close attention to their instructions. But just be expecting to get your IDs checked, to get your fingerprints taken, to not be able to take anything in the room with you. So just like what you did in the testing center here, the difference is that they're going to take you in and sit you down at the carrel. And there's going to be somebody in the room monitoring the whole time. They don't just do it by video.
With everybody that's going to be there, do we all have to start testing at the same time, or as soon as you sit down, can you start taking your test?
You can start as soon as you've logged in. You have to accept their I can't remember what it's called. It's an agreement that you're not going to cheat and that you understand you're taking a computer-based test. I think you have 20 seconds to respond to that, and if you don't respond, then they cancel your test. So make sure that you read the directions quickly and carefully and just follow the directions.
Will we log in with the same username and password as we have done for the HESI at the testing center?
No, you won't log in. They'll log you in.
Okay.
The username and password you created for HESI was just through Elsevier, and the testing center doesn't, or the Pearson VUE testing center doesn't use Elsevier test. So that wouldn't work. So everybody ready?
Yeah,
Go.
Feeling good?
Feeling too bad?
Ready to be registered technologists?
Ready, but nervous.
Of course you're nervous. If you weren't nervous, then I would be worried about you. You should be nervous, but you shouldn't be overly nervous. You should be anxious. Because a lot is riding on the test, but if you just do what you have been practicing, you will be fine. So don't put too much pressure on yourself. Remember, like I told you last time, you don't have to get every question right. So if you, as you're taking the test, read the question, read the choices, try to eliminate at least 2 of the choices, pick the best answer of the remaining choices, and move on. If you don't know the answer, do not spend a lot of time there. I noticed that. I watched you guys take your tests on Tuesday. I watched a lot of you take your tests, and I would see you get hung up for several minutes on the same question. Don't do that. If you don't know the answer, guess and move on. If you want, you can flag the question and come back and look at it later. But if you're spending more than a minute or 2 on a question, you're not going to finish. So guess and move on. It's okay to guess. It's okay to guess. Now, if you're guessing every single question, that's probably a problem. But I don't think you're going to be doing that. Don't try and race through the test. Take your time. But don't take more than a couple of minutes on a question. Okay?
sounds good.
All right. Had enough?
That's all I can think of to ask.
Okay, good. That was a good number of questions today. All right, then don't forget to let us know. Email me your results, and you don't have to even tell me your score. Just say yay or just say ooh. but you're all going to say, yay!
Don't hear from me. You know why, Roger?
All right, Roger. Well, thanks you for all your help.
All right. Thanks for being a good class, guys. We've had a fun time with you.
Yes, thank you, Roger. Appreciate it.
You're welcome.
Yeah, thanks, Roger.
Thank you, Roger.
You're welcome.
Thanks, Roger.
All right. We will see you soon, I hope, out there in the working world. Bye, guys.
See ya.
Bye.
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 Bye, Roger. Thanks.